For decades, computer science relied on an imperative structure. A programmer wrote rigid instructions, and the machine executed them. Deep learning replaces that hard-coded logic with calculus-driven optimization across interconnected nodes. At MIT, this architecture is defined as differential programming. Instead of writing fixed rules, engineers build a software architecture with parameterized sections. They then deploy a gradient-based optimizer to automatically tune those parameters against a dataset until the system produces the correct output. The network learns through mathematical optimization. It is a mechanical process of iterative adjustment, not a biological replication of the human brain. Every deep neural network reduces to two interlocking mathematical operations repeated over and over: linear transformations followed by pointwise nonlinearities. The first operation is the linear component, z equals wx plus b. This step takes an input data vector, multiplies it by a matrix of weights, adds a bias term, and projects that data into a weighted mathematical space. That projection is then fed into the second operation, y equals g of z. This is the nonlinear modifier function, which warps and thresholds that newly projected space. Stacking these two algebraic operations repeatedly forms the framework powering all modern AI systems. A single linear transformation acts as a basic classifier. If your data is simple, like these isolated red and blue clusters, a straight line separates the colors perfectly. Updating the weights and biases rotates and shifts this linear boundary until the separation is optimal. But real-world data is rarely that clean. Consider the XOR problem, where categories occupy a diagonal configuration that isn't cleanly separated. No straight line can successfully divide this quadrant. The linear model constantly fails. Simply stacking multiple linear layers doesn't solve this. The multiplication of multiple matrices collapses back into a single linear equation. Without a mathematical interruption between layers, a network is blind to the nonlinear complexity of the real world. The required interruption is the pointwise nonlinearity, the activation function. This step function is flat at 0, then jumps to 1. It fails because its lines are horizontal, a slope of 0. Since backpropagation needs a slope, a 0 gradient halts training. To fix this, researchers used the tan function's smooth S-curve. Yet tan suffers from gradient saturation. At extreme values, the S-curve flattens out, causing the training signal to vanish. The current industry standard is the ReLU, defined as the maximum of 0 or the input value. ReLU is superior because it perfectly preserves the gradient for all positive values. Its constant slope vastly accelerates how quickly a model converges during training. Selecting an activation function is a survival tactic to ensure the training signal makes it all the way backward through the network. Feeding a linear transformation through a ReLU activation creates the first layer of a deep network. This ReLU operation takes the flat plane and folds it upward into a ramp. A second linear projection creates another ramp, oriented differently. The intersection between these ramps forms a complex boundary, essentially carving a new shape out of the mathematical space. By combining hundreds of these individual ramps, the network can tessellate the entire space. It works like a 3D Riemann sum, where countless small, local shapes are aggregated to approximate any global surface, no matter how jagged or complex. This is the logic behind the universal approximation theorem, which states that a network can theoretically map any function in existence. While a single hidden layer could do this if infinitely wide, engineering reality favors depth. Stacking narrow layers requires exponentially fewer parameters to achieve the same boundaries as one massive layer. Depth provides the leverage required to fold and carve space around complex data points. When a digital image is fed into the network, its raw pixel values enter the first mathematical layer. The earliest layers learn low-level abstractions, such as sharp edges and simple gradients of light. Intermediate layers combine those edges to identify textures and geometric patterns. The final layers synthesize these into high-level concepts, such as recognizing a clownfish. A softmax function at the output layer converts raw scores into a normalized probability distribution. Architectural depth is the specific mechanism that allows the network to bridge the gap between raw color values and human recognition. Training requires cross-entropy loss, which measures the distance between the model's prediction and the ground truth label. This loss is pushed backward through every layer to update the weights via the chain rule. This involves millions of parameters wiggling and adjusting simultaneously until the total loss collapses. This scale is enabled by GPUs, which are built to perform massive parallel tensor multiplications. This massive scale challenges classical statistical theory, which assumes that over-parameterized models will simply memorize the data and fail to generalize. But we now observe double descent. Past a specific capacity threshold, the network enters an interpolating regime, where generalization actually improves. This happens because an over-parameterized model has infinite ways to fit the data. Stochastic gradient descent naturally biases the network toward the smoothest of these solutions, finding a rule that connects the data points with a clean curve rather than a jagged overfit line. By favoring these smooth functions, massive networks avoid the spikiness that ruins smaller models. At this scale, increased parameter depth becomes the very thing that enables the system to find the simplest possible rules for the real world.